Welcome back, focused learners. Let's jump right in, shall we? Today's explainer is going to be a really fascinating, progressive zoom-out journey into the entire world of coding. You know, code is basically the invisible infrastructure of our modern world. It literally powers absolutely everything, from the traffic lights in your city to global financial markets, and of course, the very device you're using to tune in right now. Understanding how it works from the micro to the macro is absolutely crucial, whether you're looking to actually build the future yourself or if you just want to understand this rapidly changing world around us. So we're going to start at the absolute microscopic level today. We'll look at the tiny, fundamental building blocks of code, and then we're going to continuously zoom out. We'll explore the languages those blocks create, the educational paths to learn them, the incredibly diverse careers they power, the massive security challenges that pop up at scale, and finally, the macro future of the entire tech industry itself.
Here's our roadmap for the explainer. We'll hit 1. The building blocks, 2. Languages and paradigms, 3. Boot camps versus college, 4. Careers in coding, 5. The security challenge, and wrap up with 6. The future of code.
Okay, moving right into part 1, the building blocks. Understanding the atoms of code.
Let's strip everything away for a second and look at the absolute fundamental atoms of this whole ecosystem. At its core, computer programming is simply the process of giving a computer instructions. But here's the catch. Computers, at their absolute lowest hardware level, really only understand machine code. And that is just long, dizzyingly complex patterns of electrical signals, represented as ones and zeros. Now, writing out millions of ones and zeros would literally take a human being a lifetime just to perform a basic calculation. No way we're doing that, right? So programming languages act as this essential bridge. It's kind of like a highly skilled diplomat translating a really complex, nuanced human treaty into rigid, unbending mathematical logic that a machine can actually digest. These languages allow us to write instructions using our human logic, which a compiler or interpreter then translates into that machine code so the computer can execute the task seamlessly.
And to write those instructions, programmers rely on a few universal concepts, really no matter what language they happen to be using. Think of a variable as just a labeled box where you store a little piece of data. It could be a user's name, their high score in a video game, or their account balance. Then we have conditionals. These are the decision makers. This is the if statement logic that checks if something is true before taking action. Every single time you log into your bank account, a conditional is running in the background checking if your typed password matches the stored one before letting you in. Loops, like a while loop, are super handy because they let you run a piece of code repeatedly without having to type it out 100 times. If you've ever scrolled infinitely through a social media feed, you're experiencing a loop, pulling new posts over and over again. Then there are comments, which are just human-readable notes left right in the code for other developers, explaining what the logic is doing. The computer totally ignores them. And finally, debugging. This is the inevitable and, let's be honest, sometimes really frustrating process of hunting down and fixing the mistakes, or bugs, you make while writing all this stuff out. Let's step back a bit to section 2, languages and paradigms, the molecules of tech.
Zooming out from the atoms, we find the molecules, programming languages themselves. Based on the TIOB index from August 2026, which tracks global language popularity, Python is sitting pretty firmly at number 1 with an impressive 18.53% rating. So why is it so incredibly dominant? While Python features a highly readable, almost English-like syntax that significantly lowered the barrier to entry for millions of people. It's immensely versatile. I mean, it's the go-to language for data scientists analyzing trends, AI professionals building neural networks, and everyday web developers alike. Trailing behind it are legacy powerhouses like C, C++, Java, and C#. Now, these languages might be a little bit harder to learn, but they offer unbelievable raw performance. They serve very distinct roles in everything from building ultra-secure back-end banking systems to running the embedded applications inside your car, or, believe it or not, even your microwave.
But building software isn't just about picking a popular language. Developers also have to choose different architectural styles. We call these paradigms. A recent study actually compared the impact of building a digital wallet system using object-oriented programming, or OOP, in a language called Kotlin versus functional programming, or FP, using a language called Scala. These paradigms fundamentally alter how a system's architecture behaves. Picking a paradigm is a whole lot like choosing whether to build a house out of brick or out of wood. It dictates everything from how easily you can add structural extensions down the road to how different teams of contractors, or in this case developers, will interact with the codebase. Object-oriented programming might focus on packaging data into distinct modular objects, whereas functional programming focuses on really clean, predictable mathematical functions. And this isn't just theoretical. The choice directly impacts real-world business efficiency, maintenance costs, and how fast a tech company can actually pivot to meet new market demands. All right, moving on to Section 3, boot camps versus college degrees, choosing your path. So we know the code and we know the languages. But how do aspiring developers actually learn all this and get into the workforce? Well, there are two primary paths today, and the data paints a very clear objective contrast between them. On one side, we have the coding bootcamp. Picture an intense, high-pressure environment spanning just a few months, costing on average around $13,580. It's heavily focused on practical, immediate skills designed to get you into the workforce as rapidly as possible. On the other side, we have the traditional four-year computer science degree. Picture a theoretical, foundational, slow-burn exploration of algorithms, computer architecture, and higher-level math. Now, it is highly respected by employers and builds incredibly deep problem-solving skills, but it certainly comes with a steep price tag, averaging roughly $35,850 per year for private tuition alone. When evaluating these two educational options, the financial math is quite eye-opening, 626.8%. Let that sink in for a second. That staggering number represents the potential one-year return on investment for a coding bootcamp graduate. How do we get that? It's calculated by taking a median salary software developer job, which is around $109,000, subtracting the $15,000 initial bootcamp investment, and dividing by that cost. Think about the macroeconomic impact of this for a moment. A 626% ROI makes coding bootcamps one of the absolute most powerful engines for rapid socioeconomic mobility in the modern economy. It entirely disrupts traditional educational timelines. Now, sure, while a four-year degree might yield higher lifetime earnings and that broader knowledge base necessary for really complex engineering roles, the short-term ROI of a bootcamp is just incredibly potent for someone looking to completely change their life and career trajectory in under a year. Okay, Section 4, Careers in Coding, the Professional Organisms. So you've put in the work and learned to code. What happens when you actually enter the workforce? The Bureau of Labor Statistics tracks these outcomes, and honestly, the median salaries are highly lucrative. But what I want you to notice is how incredibly diverse these roles are. You've got product managers pulling in over $169,000. Their job is to oversee the massive product vision and really understand user needs. But their vision sometimes clashes with the software engineers, earning around $132,000, who actually have to push back on unrealistic timelines to build the applications properly. Then you have data scientists identifying trends in massive amounts of user info, and those insights often drive what the web developer ultimately builds on the front end. All the while, systems administrators are keeping the servers running smoothly, and cybersecurity analysts are defending the entire network. The takeaway here is that coding isn't just one isolated job of someone sitting in a dark basement. It's the foundational soil for a really rich, interconnected ecosystem of distinct professionals who all rely heavily on each other to bring technology to life. Let's zoom out again. Section 5, the security challenge, protecting the ecosystem. Now, when millions of lines of code interact on a global scale across all those different teams we just talked about, the ecosystem becomes incredibly complex and sometimes very, very fragile. Recent industry surveys point out some major common web vulnerabilities. SQL injection is present in 85% of reported vulnerabilities, followed really closely by cross-site scripting or XSS at 78%. But what does that actually mean for us? An SQL injection is basically like tricking a database into just handing over its master keys by typing a sneaky, disguised command into a simple, everyday login box. Because the code wasn't written defensively, it misinterprets that sneaky text as a legitimate administrative command. These injection flaws completely dominate the global threat landscape right now, allowing bad actors to steal data, alter records, or just take down massive systems entirely. But it begs the question, right? Why are these seemingly preventable vulnerabilities still so incredibly common? Well, research points out that these aren't just technical failures, they're organizational ones. The root causes are often insufficient developer training, a lack of management commitment, and competing business priorities. Let's talk about those competing priorities for a second, because it's important. In a high-pressure corporate environment, security is often entirely invisible right up until the exact moment it catastrophically fails. New features, on the other hand, those drive immediate revenue and user growth. This creates a really dangerous misalignment in corporate incentives. In these high-pressure DevOps environments, the push to deliver shiny new features faster often results in secure, defensive coding practices being completely bypassed by exhausted development teams. And finally, Section 6, the future of code. Where are we heading?
We've zoomed out from the individual variables in code all the way to global organizational security challenges. Now, let's zoom out one final time to the macro level. Where is the entire field of programming actually heading? A huge trend on the horizon is the explosive rise of low-code and no-code platforms. We're talking about platforms like Zoho, Salesforce, and AppSheet that offer user-friendly visual interfaces. They have drag-and-drop functionality and reusable pre-built components. What this means for you is that very soon, you might be building complex, custom enterprise software to automate your daily job without ever having to learn the atoms of code we discussed back in Section 1. It completely democratizes development. It allows everyday business users to build integrations visually and bypass traditional manual coding entirely for a ton of corporate use cases.
Simultaneously, artificial intelligence, specifically large language models, are stepping right into the development pipeline. LLMs are actively being used right now to provide early feedback, evaluate syntax, and even generate code snippets to automate security. Think of the AI as a highly capable co-pilot for developers. And it's not just about auditing for security flaws, it's about AI writing the tedious, repetitive boilerplate code. This frees up human developers to focus purely on the high-level architecture, the creative problem-solving, and building much better user experiences. Now, while AI cannot entirely replace the nuanced review of a human expert just yet, it is fundamentally reshaping how code is written, audited, and deployed across the world.
So as we look at these massive macro trends, it leaves us with one final, pretty provocative question to ponder. Will AI and low-code platforms eventually replace human developers altogether, or will they simply redefine what it actually means to write code in the future? It's a fascinating paradigm shift for sure, and the answer will likely shape the next century of human progress. Thank you so much for joining me on this explainer today, Focused Learners. Keep exploring, keep zooming out, and I'll catch you on the next one.